The world's greatest athletes were not trained overnight, and the world's greatest athletes do not train without data. Today, even lay people have access to biometric data all day through their modern smartwatches.
How does this thing even work? It tracks my steps and my heart rate all day, whether I need it to or not.
Today, we shall uncover how optical heart rate monitors and how smartwatches track cadence by creating devices using circuit elements taught in ES50.
We made a heart rate monitor and a cadence monitor. How does it work? Let's start with the heart rate monitor. Here's the machine. It uses a sensing and emitting photodiode to emit light into your finger and sense the light that is reflected back. The volume of the blood in your finger fluctuates slightly with each heartbeat. This fluctuation causes a change in the amount of reflected infrared light, which is picked up by the photodiode sensor. We can use the signal to determine a pulse by filtering the signal with the proper conditions.
Our circuit takes the signal from the sensor, passes it through a low-pass filter, and amplifies the signal, which removes high-frequency noise from the signal. Then it goes through a second-order bandpass filter and is once again amplified. This filter ensures we only have the desired signal before the signal is fed into a comparator to convert the signal into a digital 1 or 0.
Next, we needed a way to display the heart rate. We were inspired by the ECG graphs on Apple Watches, which show a few seconds of history in real time. We chose to use 3 0.8-inch displays, each with 64 dots for a total of 192 LEDs. This posed a difficult challenge since there are not 192 output ports on the Arduino. We needed a way to divide the signal and output a useful image to the screen. On the display, we have 4 seconds of real-time heartbeats displayed. The top row of LEDs is reserved for displaying an approximate heart rate zone, which is calculated every 10 seconds. We decided to use shift registers to divide the signal output from the Arduino. The shift registers turn a single input into 8 outputs that update based on a latch signal. Since we want to update all of the LEDs at the same time, all of the shift registers can share the same latch as well as clock signal. Here's how the circuit came together. We have the power, ground, clock, and latch signals. Here we have 3 input signals as well. The shift registers are implemented in sets of 2, where each set corresponds to rows and columns for one display. Next, we attach the outputs of the shift registers to the displays using the documentation provided. Now we just have a coding problem to solve in order to produce a useful output.
It isn't all about heart rate though. While on a run, the device helps keep track of cadence or steps per minute by playing a series of tones that increase in tempo when the runner accelerates, or vice versa.
The main component is an Arduino 9-axis motion shield, which measures acceleration in 9 directions. Every time the user takes a step, their vertical acceleration changes direction. This is visualized as a peak in the acceleration data. The acceleration is temporarily stored in an array where the data is processed such that the number of peaks in the data corresponds to the number of steps the runner takes. This process is repeated in intervals of 3 seconds where roughly 600 data points are collected by the accelerometer. Each time the cadence is measured, the tempo of the beeps is reconfigured depending on the range within which the threshold is found. What this means is, as the runner speeds up or slows down, the rate at which the beeps play increases or decreases to follow their cadence.
Thank you so much to Chris and Marko for an amazing semester, to Addison and Isa for their role as group advisors, to David Abrams for providing photodiodes and lab instructions, and to all of you for watching. You make our hearts beat.